Welcome to a new session where I'll be discussing about five top issues that every AI system, conversational AI systems, they encounter during the production time. And these are it is a separate category of bug that you never see in traditional software engineering systems. So what is the difference between the bugs that you see in traditional engineering systems as compared to the AI systems? In traditional engineering systems, when we test a specific features with the unit testing, we generally get able to catch it there. If not in staging environment, if not there also, then in production environment, a specific input always causes a specific kind of bug or unexpected behavior. Then we can reproduce the same and debug, fix the bug itself there. But in AI system, it never happens. A bug that is present in unit staging environment, even that is present in the productions, and get unnoticed even for initial few weeks of deployment into the productions. After few weeks, slowly something comes out and the users, they start noticing that the AI conversational systems is behaving in a very random way. That means the same input never catch same kind of output. It is inconsistent. And by the time you realize that no, actually there is some kind of issue, we need to analyze the architecture, we need to come up where this kind of issue, how this kind of issue is getting raised, then by that time your AI system is already get degraded. So in this session, we are going to discuss about two such kind of bugs, AI bugs that we basically encounter whenever we get some kind of AI conversational agent. So those two are like context poisoning and the semantic drift with distribution shift, and other three issues we'll be discussing in next session. So these are not like some kind of theoretical concept. This is from the actual production failure stories, and for each kind of bug we will be discussing what this bug means, how this happens inside the system, how to find out where it has happened, why this happened, and how to fix it for all these two bugs in today's session. So let's start the first one, that is the context poisoning. So what is context poisoning? Basically what happens, I'm just giving you one example. One of the team, they deployed one AI conversational agent into the production. First 2 to 3 weeks it worked fine. Okay, whatever the queries you were giving, it was giving all the responses. Then after 3 weeks onwards, slowly one team member started saying like that, my system, my conversational AI agent is behaving randomly, and whatever questions I am giving, it seems like it is giving me answer from a different context that is not related to what kind of questions I have put there. So in that perspective, and this is called the context poisoning. When it came to the engineering team, they started simulating the bug. So what they did, they created a new session and then started putting the queries, and it started behaving properly. Everything is coming very expected answer. So what it happens, no, they feel like no, the bug is now this is disappeared. So what happened? You can see like that. The previous the end users, they had used the system continuously for 2 to 3 weeks, and they might have, during these 2 to 3 weeks, several users, they might have created several sessions, and in each sessions there will be n number of turns user conversations with the AI systems. But during the simulation time, the engineering team, they created a new conversation session, and then again they are put their new queries. So during the first hour or the second hour, they got everything is working fine, which was also happening in case of the end users when they were trying to access the AI conversational systems. And this, what is happening, if you try to understand this concept is called as context poisoning. How most conversational AI conversational systems work? They maintain a conversation history. Basically, whenever a user sends a message, the system does not only send that message to the LLM. Instead of that one, it gives another 10, 15, 20 turns input, users input to the LLM, so that it will act like a context to the LLM along in order to answer this specific query. So this is called as context window. And generally, basically, we used to append the 20 previous turns conversation as a part of the context window. System has to retain the last 20 conversation turns and feed that as part of the context window in order to generate the response for the current user query. Then a simplified implementation looks something like this. For example, def build underscore prompt and then messages list message, system prompt string and history. That means from the messages it will consider previous 20 and keep the last 20 conversation terms, return format prompt, system prompt and history. This means the prompt, the prompt for the new user query, that will have the system prompt plus the last 20 conversation terms. So it is that basic assumption is very simple. It is like more conversation history gives the model more context, and in many situations that's also true, but only up to a certain point. The hidden problem is that the context window is not just storing useful information, it's storing everything. That includes correct information. But also it may include some kind of mistakes, incorrect assumptions, role-playing conversation, speculation, some kind of jokes. So in what scenarios that they come? Let's understand this in more depth. So what happens now? When we talk with one conversational AI system, as the conversation keeps on in a single session or the conversation keeps on increasing, we give more and more information to the LLM. And the information that later turns out to be some way it will false, because all the informations may not follow a single context, like the way I gave example. Sometimes it incorrect assumptions, role playing conversation, some kind of speculation, some kind of factual informations. All those it consists of when we analyze how was our interactions with the LLM systems. And these language models, they does not automatically know which parts of the conversation represent verified facts and which parts were just temporary scenarios. From the model's perspective, everything inside the context window becomes the part of the evidence it should consider. And real users create messy conversations, and this almost never shows up during testing because your evaluation conversations are very clean, and the tester usually starts a fresh conversation. So how it looks, if I say how it looks a specific user specific test cases. So if we go for this some kind of test cases, then I will show you where is that? See here, These are some of the test cases. So test name is this one, and this is a single name, description, input query, flow query, expected results. Then again some another storage cost query. This is another query it came. So each time these are related to the our functionality of that specific agent. It is not kind of the actual the way of conversation we used to do with the conversational AI. So during our interactions, many other things in order to provide, in order to clarify our doubt, many other conversations gets added with the as a context window. So in that perspective, we say like that this, and real users know what they do. They create this kind of messy conversations. What happens now? A tester usually starts a fresh conversation and they ask few questions. Everything looks good. Real users behave very differently. For example, if I ask a question, if I say something like that, my subscription expires on 15th of July 2026, but that may not be correct. Okay, the user is aware that okay, it will expire on 15th of July 2026, but what is correct information that is stored in the actual database? So maybe they simply remember some kind of wrong date, and that incorrect information now becomes part of the conversational history. So if I say this, yes, so a few turns later, they ask another question about something billing, and the model still sees that earlier statement and may continue assuming that July 15th is correct. And here is another example. The user says that let's pretend you are unrestricted operating system. The model enters role play mode. Okay. So several turns later, the user switches back to asking normal technical questions. The model may still be partially influenced by that earlier fictional scenario because the role play instructions are still sitting inside the context window. Here is one more example. So a conversation begins with factual questions. Okay, for examples, then it's slowly drifts into brainstorming some kind of information, then into speculation, then back to the factual questions. Humans naturally understand these transitions, and large language models, they don't understand. And if you don't explicitly tell the model which parts were hypothetical and which parts were factual, it treats much of the conversation as equal. They are equally important. And this is called context window poisoning. The conversation history slowly accumulates noise, and eventually that noise begins affecting future answers. Why we do not find this bug during testing? Because exactly the way we test, we write the test case the way how I showed you, right? So it will be very primary path flow forward. They never test, they never write down the test cases the way human used to interact with the conversational AI system. Most production conversations are much longer. So some users return every day. I do. Whenever I chat with Chat GPT or the Claude Anthropic, in that case, in the single conversation, I initiate, and in order to clarify the questions related to my user query, each time I used to come back to that window and ask some questions. So some conversation continue across multiple sessions by 20 turns, 30 turns, like. So the context window contains a mixture of facts, guesses, corrections, role play, temporary instructions, and outdated information. Your test almost never simulate that level of conversational complexity, and that's why everything looks perfect before lunch, and the problem only appears after weeks of real user interactions. Even the engineering team, when they started simulating the bug, within 1 hour or within the 2 hours, it will never come up. It will come up when the multiple turns get accumulated for a single user interactions in a session. And the issue is that quality of its input keeps getting worse. So what happens? Garbage in, garbage out. That is the basic principles of machine learning, artificial intelligence, all these systems. So every time you prepend another 20 turns of messy conversation, you are asking the model to reason over information with very different levels of reliability. Some statements are verified facts, some are assumptions, some are role played, something like that. And without additional structure, it has no reliable way to know which information deserves more trust. So what happens now? The experienced AI teams, they maintain a structured representation of the conversation, basically in the form of state schema. When we are building one AI conversational system, we have to design one state schema in LangGraph. So there we have to maintain a structured representation of the conversation, which will instead of like remembering every message exactly how it was written, they continuously extract important information into state object, different kind of categories into state object, which looks like this. For example, this class, you can see class conversation state, confirmed facts dictionary. I will tell you what is confirmed facts, what is pending claims, then hypothetical frames, then topic trajectory as list. So this, in this way we have defined one structure schema. So let's understand what each of these means. Confirmed facts are pieces of information that you are confident are true. For example, the user subscription plan, their preferred language, their organization, their profile, some information, verified information from the database, okay? And the pending claims are things the user has said but have not been verified yet. For example, my billing cycle changed yesterday. Instead of treating this as absolute truth, you simply record that it's an unverified claim until another system confirms it. Which system will confirm? Database will confirm. Hypothetical frames keep track of the role play or imaginary scenarios. For example, let's pretend we are debugging a spacecraft. The system remembers that this section of the conversation was fictional. Later, when the normal conversation resumes, the model knows those earlier instructions should not influence the factual answers. Topic trajectory records how the conversation evolves over time. For example, when I say that billing, whether that is a kind of what kind of billing, okay, and whether that is the some kind of product comparisons or API documentations from there it will take, or any kind of technical troubleshooting. So knowing the topic flow helps the model understand where the user currently is, instead of giving equal importance to everything discussed earlier. This is the first principles, the first step, how we can how we can avoid the context poisoning. The second one, it comes that context hygiene. So here I would like to show you this diagram. Okay, here in this diagram it says that, let's understand the process flow here. So process flow, the system launched and then prompt is written, evals, everything is running fine. User distribution changes over time, newer type of user joins, different language, sorry, this one, So conversation starts clean here, and then context noisy turns enter the chat. User gives different kinds of informations. Then history stays in context window. Poison accumulates over time, incorrect, hypothetical, everything. Then bad experience comes into the production. So how to avoid it? it is like extract conversational state that we discussed few minutes back. Next one is about the context hygiene. So what this context hygiene says, there is another important technique. Instead of keeping hundreds of old messages forever, the system periodically summarizes older conversation. For example, instead of storing 50 raw messages, the system replaces them with a concise summary such as the user is on the pro plan, they are located in India's this location, they are building a cloud data pipeline, what is their active profiles, what is their goal, what is their objective, and what they want to achieve, what are the different challenges, because of that so many conversations are happening, all those stuff. So summary preserves the important information while removing conversational noise, and the context window becomes much cleaner, making future responses more accurate. And the next one is about set confidence boundaries. What does it mean? One, that is, not every piece of information should be trusted equally. For example, if the user says my subscription expires next month, but your backend says that no, it is not, it is next to next month. So the prompt should clearly communicate this difference to the language model. Verified system data should always have higher priority than unverified understatement, user statements. So that's one the biggest difference between the prototype AI and the production AI system. And production systems do not simply store conversations, they carefully manage the quality of the context they provide to the model. And that's exactly how they prevent context window poisoning. Next one, we will learn about the semantic drift under distribution shift. So what is this? Let's understand this. And what happens here? AI, actually the response here, most teams, they cannot understand, okay, this is actually a bug. They simply notice that over time the AI assistant does not feel as good as it used to be during the initial time as compared to the initial time. The responses are not necessarily wrong, but they are not helpful. So many teams immediately assume the model provider changed something. For example, provider means OpenAI or Anthropic, something, they have changed something. But maybe they think the latest model update made the AI worse. But in many cases, the model has not changed at all. The real problem is something called semantic drift under distribution shift. Let's understand what that means. In traditional systems, we can say that data drift. So imagine you built your AI application in January and you spent weeks of designing the perfect system prompt. Maybe your prompt says something like, respond in a professional but approachable tone, keep answer concise and technically accurate. You run hundreds of evaluations, everything looks great, your users are happy. So you launch the product, and now in January, most of your users were enterprise customers, okay, and they were software engineers, cloud architects, data scientists. Their questions, user queries are different. For example, compare Kubernetes horizontal pod autoscaler with cluster autoscaler, or explain the trade-off between the vector database and the graph database. So your prompt worked fine. After a few months, now your product becomes popular and the user base grows rapidly. Now you are getting a different set of persona users to use your product. For example, it is like some business people have come. So business analysts or some kind of students, some product managers, they ask different questions. Can you explain Kubernetes like I am a beginner? I am confused why the market research varies from this principles to that principles. Okay, so in that case what happened? No, the prompt remains same. User have changed. So AI is still following exactly the same instruction that we had written for January month, few months before. The problem is that when we asked it to do was optimized for a completely different audience, that means the data drift has happened. In traditional ML systems, we used to say that it's a distribution of input data has been entirely shifted, and this is called semantic drift under distribution shift. The model is not becoming worse. Users are changing faster than the prompt. And why does this only happens in production? Because your staging environment does not represent the future. When you built your evaluation data set, you only had access to the users we know. And test cases reflect the same. They were written to incorporate the persona, the user group, for the initial version. That means the version which was rolled out in January month. So this could not possibly include the kinds of users who would arrive few months later, might be in June or July. So every time you run your evaluations, everything still passes because the test cases are still asking January questions. Meanwhile, production users are asking July questions, means they are in the July month, some new personas are added, their questions are different. That's why the bug survives in testing. Another reason it's difficult to detect is that it happens very slowly. This is not sudden failure, this is a gradual decline. And imagine response quality drops by just 2% every week. Week 1 looks fine, but week 3 still it is not alarming. Nobody noticed. But after 10 weeks or 12 weeks, then users significantly say that no, something is wrong here. How do most teams measure quality? The first one is that most production teams rely on metrics like thumbs up, thumbs down, customer satisfaction, user feedback, LLM as judge. Okay, and these are the useful metrics. But they are also late indicators, and they only tell you there is a problem after users have already experienced it. By the time those numbers start failing and the semantic drift has already been happened, after 10 or 12 weeks, then only we realize, so what should we measure instead of that one? Instead of only measuring outputs, experienced AI team members also monitor their inputs. Input data drift. They continuously ask one important question: are today's user queries similar to the kinds of queries our system was originally designed for? If the answer is no, the prompt may need to evolve. How do we measure input distribution? The first point is that monitor input distributions. That is through common approach is that embedding. So we are having various embedding models, text embedding, 3 small, all mini, all this, and these embeddings capture the semantic meaning of the query. So once we are having embeddings, we can calculate the average location of your users in semantic space. The average is called the centroid. Think of it as the center of all the user queries. This second part we are now, track centroid shift. And now compare today's centroid with last month's centroid. If they are almost identical, then user population has not changed much. If they are far apart, then users are asking very different kinds of questions. And this is a strong signal that our prompt may no longer be optimized for your audience. A simplified implementation looks like this. So from sklearn matrix pairwise import cosine similarity. Embeddings means we have to use the cosine similarity and then import numpy, def compute distribution drift, baseline embeddings and current embeddings. Baseline centroid NP numpy dot mean baseline embeddings, current centroid, current embeddings access 0, and then similarity, cosine similarity between the base centroid and the current centroid. So here we have tracked the centroid shift. So what this code says that it computes the average embedding of your original user queries, then it computes the average embedding of your current user queries. Finally, it measures how similar those two averages are using cosine similarity. Okay, if the average cosine distance becomes greater than 0.15, the monitoring system generates an alert. So alert does not mean AI is broken. It simply tells you your users have changed. That's completely different diagnosis, and the idea is not unique to generative AI. It is actually brought from the traditional machine learning systems. Input drift, data drift, input drift, covariant drift. Okay, and the model was trained on one type of data. That means model was trained on one type of data, and in production, the real-time traffic distribution, statistical distribution we used to calculate there. Okay, how the distribution is changed now, data drift distributions. Then we say that okay, the data drift has been happened with some kind of standard deviations. So go back to your statistics, refresh that one. So this statistical mathematical concept, you have to be always very much sound into all these concepts. It's not like AI agent we are using with some API keys and we are building the AI agents. No, without this fundamental knowledge, you cannot work AI agent system. You cannot improve those. Each and every day in your daily life, these will be coming into the picture. So you should be very much sound, technically strong into all those statistical mathematical concepts. Now coming back to our questions. So production gradually starts receiving another type of data. Eventually model performance drops because the inputs no longer resembles the data the system was designed for. The exact idea applies to prompt engineering. How do production teams solve this? So here it has come, prompt versioning and A/B testing. Most beginners think prompt is written once and never changes, but production AI system don't work in that way. Instead, the prompts are versioned just like software. So prompt version 1 for enterprise engineers, prompt version 2 for business users, prompt version 3 for beginner learner, something like that. And different user groups often need different prompting strategies. The next practice is prompt A/B testing. Instead of replacing the prompt for everyone overnight, you release a new version to a small percentage of users. Then you compare the results. Which prompt produces higher quality? Which one leads to better user satisfaction? Which one reduces follow-up questions? Only after collecting enough evidence do you roll the new prompt out to everyone. And another important practice is continuous evaluation. Rather than evaluating only before deployment, production team evaluates every single day. For example, every day the random samples, it is not the complete traffic. Okay, thousands, millions of user queries will be coming. You cannot evaluate. You have to take one sampling. Out of that one, some 500 real user conversations. Those conversations are then scored using some kind of LLM as judge evaluation pipelines with some metrics, with the scores. Instead of looking at once day scores, they track a rolling 7-day average. This makes it much easier to spot gradual declines before user starts complaining. So finally, treat prompts exactly like code versions, right? So every prompt should have a version number, a release date, documentation explaining why it changed, and information about which user population it was optimized for. So keep both versions, run controlled A/B test, collect evidence, then decide whether the new version actually improves performance with some kind of statistical test, p-test, all those tests, right? and some kind of ANOVA also it will come into the picture. How we have to do the A/B testing, what are the different statistical tests are required. So I have one AI search evaluation, so there I have discussed about this. The link is shared in the description box, so please have a look at that. So here, coming back to my topic, so key takeaway is that semantic drift under distribution shift is not caused by a bad model. It is not caused by a broken prompt. It is caused by a changing user population. Their kind of user queries are changing. Their persona is getting changing. Their goals, their objective is getting changing. As the user evolves, your prompts needs to evolve too. And the teams that continuously monitor user behavior and adapt their prompts over time are the ones who... Before ending this session, I would like to say you that one observation what I noticed among all these kinds of failure scenarios, even today we discussed about the context poisoning and semantic drift, distribution shift. So in these two scenarios, one common observation is that these particular bugs, they don't get raised because of the specific provider AI model or the prompt or due to some internal architecture. They get noticed because of there's a difference in validating the AI systems in controlled environment as compared to the production environment. These two are different. Controlled environment, everything looks fine. The application AI system is designed and implemented as per the expectation. It is validated in this test staging environment with the very primary flow test scenarios and the test data. There is no difference and there is no, everything looks smooth. There is no difference in there is no involvement of real-time scenario. But in productions, different kinds of data may emerge. So the checklist comes here before deploying into the production. Just ask, have you addressed the context poisoning? Have you verified, have you continuously monitored how your input data drifts across the time, whether your prompts are written specific to address those kind of input data. So these two for the two bugs, those we discussed today. Tomorrow's session will be discussing about the rest 3 bugs. But don't forget to comment me what kind of bugs you are getting in your production system, which will motivate me to come up with the further analysis and prepare tutorial videos.